have the Dean of Academic Affairs, Professor Apurva Sharma, and we have the Department Chair of Physics, Professor G.D. Verma. So as I had informed, there is a little welcome that would like to be done. So with your permission, Professor Witten, can we start with that?
Yes, go ahead, of course.
Okay, great. So I think Professor Sharma, please.
Good evening, everyone. Good morning, Professor Witten.
Good morning.
Right. We are very happy to be here with you. And this evening, here, very significant evening at this campus at IIT Roorkee. And we are celebrating the first Institute Research Day. And as part of this, we are organizing a couple of events here. And one of this is a series of lectures. And you are here as part of that lecture, and as well as our Department of Physics is organizing a C.V. Raman Memorial Lecture, and you are delivering this lecture as part of both of this event. So just let me give you a very brief about this Institute Research Day. So our institute is like having 9,000 plus student strength, out of which 4,000 plus is postgraduate students. And we are contributing like at various stages to the research, invariably be it you undergraduate or at postgraduate level. And just to put it a kind of statistics, like our citation per faculty in India is at the highest. So we thought like let us like celebrate one day at least in a year as Institute Research Day. And the institute has already finalized that 14th March will be this day on which every year we will be celebrating Institute Research Day. And that's how today we are here. And incidentally, this is the birthday of Albert Einstein. And also this is Pi Day, like 14.3. So that is Pi Day. So we could not find a better day than 14th March for celebrating this Institute Research Day. And I'm very happy that you are here, and all my colleagues are here. Our director, Professor Ajit Chaturbedi, is here. And I welcome you all to this event. And I thank you, Professor Alok, for coordinating this evening's proceedings. And it's up to you. May I request Professor Ajit Chaturbedi, our director, to address very briefly. So.
Good evening to all those joining in India, and good morning to the global audience joining from the Western Hemisphere. Good morning, Professor Witten. It's a real delight to be here on this occasion when we are hosting the first Institute Research Day of IIT Roorkee. Many departments are celebrating their respective research through departmental research days. An idea was mooted by some of our colleagues that it is high time that we also do it at the institute level to bring all the departments together. And the immediate benefit was visible in today's poster session when we saw that several posters in different departments are working in similar domains, which means that it will be good if they join hands to solve more interesting or more impactful problems. So the Institute Research Day provides a platform at which students from different departments can interact about their research problems, get to know who is working on which problem, and possibly find new opportunities for collaboration and addressing interesting problems. It's a real delight and pleasure that Professor Witten has agreed to deliver the lecture today. And without further ado, let me conclude here my brief address, and we all look forward to Professor Witten's address. Thank you.
Thank you. May I now ask Professor G.D. Verma, Department Chair, to please address the meeting.
Thank you, Professor Allo. Good evening to everyone, and good morning to Professor Witten. Professor A.K. Chaturvedi, Director, IIT Roorkee. Professor A.K. Sharma, Dean of Academic Affairs, faculty colleagues, and dear student. On behalf of Physics Department, I welcome you all in today's third lecture of C.V. Raman Memorial Lecture Series. The Department of Physics started C.V. Raman Memorial Lecture Series in 2018. In this lecture series, we invite well-known physicists to deliver talk of popular nature at institute level from different research area of physics. The first lecture of this series was given by Professor T.V. Ramakrishnan on emerging phenomena in condensed matter physics. Recently, on January 19, 2022, second lecture was given by Professor A.K. Sood on nature-inspired physics of life. Today, I am delighted to welcome Professor Edward Witten, who has kindly accepted our invitation to deliver third lecture of C.V. Raman Memorial Lecture Series on black hole thermodynamics, then and now. On behalf of Physics Department, I thank you, sir, and we all will be highly benefited with your lecture. Thank you, everyone.
Well, thanks very much for the kind invitation and the kind words. And it's an honor to speak on your Institute Day and also in memory of Professor Raman. So as you realize, my subject is black hole thermodynamics then and now.
Sorry, Professor Witten. Sorry, we are not yet done because I got a little bit to speak about you. You have not been used.
No need to say anything about me.
Can you please allow me to say one sentence?
Okay.
So, okay, so I think the speaker has gagged me, and I don't think I'm going to agree entirely. So, folks, I would just say this, that so as Professor Sharma told us, that we are celebrating Albert Einstein's birthday tomorrow. And of course, today we are also in some sense celebrating Professor C.V. Raman. In my very humble opinion, I think we could not have found a better speaker, a unique combination of the pure power of the flight of thought manifest, whether it is mathematics, whether it is physics, whether it is even politics. I mean, so we are so grateful, Professor Witten. And just one little thing I'm going to squeeze in. I know he's not going to like this, but he is considered, I mean, he's obviously, we all know, I think he's the 1990 recipient of the Fields Medal, which most people consider to be the equivalent of the Nobel in mathematics. And believe you me, he has very few rivals, quote unquote. In fact, his contributions to physics have in fact generated amazing ideas and developments in mathematics. So I think I will shut up now. So Professor Witten, please deliver your lecture, Black Hole Thermodynamics, then and now.
Thank you, Alok, for these additional remarks. And as I said, it's an honor and privilege to have the chance to give this lecture in honor of Professor Raman and also your Institute Day. So I'll start by reviewing some of the high points of black hole thermodynamics, which is a subject that by now goes back half a century. And then I'll tell a little bit about more modern points of view. Although it's challenging, it's a little too much to do all of this in one lecture, but we'll do what we can. So as we'll see in the last part of the talk, the more modern understanding revolves around a microscopic understanding of entropy. But there's a limit to what one can explain in a single lecture. Black hole thermodynamics goes back to the work of Jacob Bekenstein, who was a student of John Wheeler. He asked what the second law of thermodynamics means in the presence of the black hole. We could take a cup of tea and throw it into the black hole. The entropy in the cup of tea seems to disappear. So the second law is violated unless we attribute an entropy to a black hole. So that's what Bekenstein wanted to do. he wanted to define an entropy for a black hole in a way that would fix the second law of thermodynamics, so it would be always valid. The second law says that for an ordinary system, the entropy can only increase. But as I said, the entropy in the cup of tea seems to disappear. So he wanted a generalized notion of entropy. And so he wanted to assign to the black hole an entropy function that can only increase. So a first question is, what property of a black hole can only increase? It's not true that the black hole mass can always increase. By this time that was known because Roger Penrose had shown that a spinning black hole, if it absorbs matter, a spinning black hole can interact with outgoing matter in such a way that its mass goes down. Its angular momentum also goes down. And it's believed that that process actually powers quasars, that quasars are driven by the rotational energy of a black hole. So a rotating black hole can lose mass as its rotation slows down. You could make a charged black hole lose mass by reducing its charge. But there is a quantity that always increases. Somewhat inspired by work of Christodoulou, Stephen Hawking had just proved the area theorem that says that the area of the horizon of a black hole can only increase. So it was fairly natural for Bekenstein to propose that the entropy of a black hole should be a multiple of the horizon area. For example, here's the metric of a Schwarzschild black hole of mass m. The horizon is at 2 gm, so the area is 4 pi r squared or 16 pi g squared m squared. Well, since entropy is dimensionless, to relate the entropy to its area, you need a constant of proportionality with dimensions of area. From the fundamental constants, h bar c and Newton's constant g, you can make the Planck length and the Planck area LP squared. In units with c equals 1, Bekenstein's formula for the area was this one, the area over 4gh bar, where the constant 1/4 was not clear in Bekenstein's work and was provided by Hawking a few years later, as I'll explain. But the g and h bar are needed here for dimensional reasons. So for a Schwarzschild black hole, this is the entropy. Now, I usually set h bar to 1 in these slides, but it's useful here to include the 1 over h bar to explain why black hole entropy is so large. For example, if you have a black hole the mass of the sun, this formula says the entropy of a black hole the mass of the sun is something like 10 to the 20 times the entropy of the actual sun. So the 1 over h bar, g should be in the denominator. Sorry. The 1 over gh bar goes into the fact that in everyday terms, so g is very small in elementary particle standards, and of course h bar is small near a classical limit. So the denominator helps explain why this entropy is so large compared to the entropy of an ordinary body. So Bekenstein's idea was that the black hole entropy captured the information lost when the black hole was formed. He interpreted it as the logarithm of the number of possible ways to form the black hole. And he proposed a generalized second law. He defined the generalized entropy, area over 4gh bar plus the entropy outside the black hole. And the proposal was that the generalized entropy always increases. So the claim is that when something falls into the black hole, S out can go down, but A over 4gh bar increases by more. So he made a few tests of the generalized second law. Here's one, but I think it's the most interesting one. Take photons with a wavelength lambda, and therefore energy 1 over lambda, and shine them on the black hole. The entropy of a photon is of order 1, for example, because the photon has 2 polarization states. You might think that the position of the photon would increase its entropy, but it doesn't really do so by very much. So order 1 is a good estimate for the entropy of a photon that's being shined on a black hole. When the black hole absorbs one photon, its mass shifts by this amount. So its entropy 4 pi g m squared shifts in this way. So Bekenstein wanted the shift in the entropy to be bigger than the entropy of the photon that was being captured, which is of order 1. So he observed that if the black hole is capturing photons of a size smaller than its Schwarzschild diameter, so lambda is less than 4 gm, then the black hole entropy is much bigger than 2 pi, which is satisfactory. Sorry, the change in the black hole entropy. He wanted delta S of the black hole to be much bigger than 1, or bigger than 1 at least. And if the black hole is capturing photons smaller than the black hole in wavelength, then it worked nicely. But Bekenstein didn't really get a satisfactory answer if the black hole is absorbing photons whose wavelength is larger than the black hole size. That can happen, though not very efficiently. If you look at Bekenstein's original paper, you'll see that what he says about this is not entirely convincing. The question didn't really have a satisfactory answer in the framework Bekenstein was assuming, which was that whatever falls behind the black hole horizon stays there forever. In thermodynamic terms, since Bekenstein assumed that the black hole does not radiate, one should assign it a temperature of 0. But thermodynamics says that at equilibrium, the change in the energy E and entropy S are governed by dE equals TdS. So a system with temperature 0 should have ds equals infinity if dE is non-zero. But Bekenstein wanted the black hole to have a finite, not infinite entropy. So his setup wasn't really consistent with assuming the black hole had 0 temperature. And that's why he had trouble understanding the interaction of the black hole with photons of very long wavelength. In hindsight, you'd say that you can't analyze properly the absorption of very long wavelength photons by the black hole while ignoring the fact that the black hole is strongly emitting such photons. Famously, Stephen Hawking discovered a couple of years later that at the quantum level, a black hole is not really black. It has a temperature proportional to h bar. He discovered this by analyzing the behavior of quantum fields in a black hole geometry. The picture I've drawn here is called a Penrose diagram. And probably many of you are at least familiar with the basics of Penrose diagrams, but some may not be. So I want to take a little bit of time to explain the idea. First of all, spherical symmetry is assumed. So the angles are suppressed. And what's plot is only time and also the distance, the radial distance from the origin. So in the picture, time runs vertically and space runs horizontally, roughly. But following Penrose, it's very convenient to pick conformal coordinates where, first of all, infinity is at a finite distance so you can see it. And secondly, light rays travel at 45-degree angles. I haven't drawn that perfectly, but light rays are at a 45 pi over 4 angle from the vertical. So for example, this particular line here, which is meant to be at a 45-degree angle, is the horizon of the black hole. If you're outside the horizon, then at a 45-degree angle, you can escape to infinity, which is up here. If you're behind the horizon, even trying to escape at a 45-degree angle, you end up at this wiggly line, which represents the black hole singularity. The red is the matter of the incoming star. It starts at past infinity, which is way down here. The picture makes it look like the star comes from a point, but actually, to draw this diagram so we can see it, an infinite amount of space in the far past has been mapped to that point. The star lives for a while and then it collapses behind the singularity. And when that's happened, anything outside the black hole horizon can't escape because even at a 45-degree angle to the vertical, it will reach future infinity, which is up here. So future infinity is where a physicist sits with a laboratory measuring what might be coming out of the black hole. And the very future of future infinity is up here. So let me give this point a name. The far future is up here. If you're sitting outside the black hole with your laboratory making measurements, you're not really at future infinity, you're just far away. So you're doing something like this. That's the world line of the observer. So I hope I've said enough. Well, okay, once again, many of you will be familiar with such diagrams, but I hope I've said enough so that if you're not, it'll help you make sense of the rest of the discussion. So the measurements an observer makes at future infinity can be traced back to initial conditions of the quantum field, or classical matter if there was any, on a Cauchy hypersurface. So I've drawn here a space-like hypersurface called a Cauchy hypersurface. Actually, it might have been better to draw it so it continues way out here, which this point here is called spatial infinity. But regardless, that part of the surface won't be important. The part we will care about is the part near the black hole. So you can imagine if you're sitting up in the far future and making measurements up here, whatever you observe up here consists of particles or fields that is determined by initial data on this blue hypersurface. If you were behind the black hole horizon, you'd also see initial data on the part of the horizon, on the part of the blue hypersurface that's behind the horizon. But for an observer who's outside the horizon, you can only see part of the initial value surface, namely the part of this blue surface that's outside the black hole horizon, outside of this horizontal, slanted line. So here, what I've drawn in this picture, in purple, these are meant to be parallel lines, all parallel to the horizon. They represent signals traveling outward at the speed of light and going toward this region up at infinity where the observer lives. So the observer up here is seeing these signals that travel outward. Well, they might travel slower than light. You might see a massive particle, but the most rapidly escaping signals from the black hole are light rays that will travel on these purple lines up to infinity where they get collected by the observer. Now we want to ask what an observer will see. Part of Hawking's insight was that although the full details of exactly what the observer will see depend on the details of the collapsing star, if you ask what the observer will see in the far future after transients die down, there's a universal answer. The most important point in the picture is that a signal that's received very late, so a signal that the observer sees very close to this end of future infinity, originated from very close to the horizon. If the signal is going to reach the observer way up here, it had to originate right near here. So the observer who's sitting at a great distance in the far future, seeing what comes out of the black hole, is seeing things that escape from very close to the horizon. So you see, let me explain in another way, apart from this picture, why that's true. You know that if something is behind the horizon, it will never escape. If instead you start from outside the horizon, you can escape, but the closer you are to the horizon, the longer it will take. So if you wait a very, very long time and then collect whatever might be coming out of the black hole, you'll be collecting the things that start from very near the horizon and therefore escape very late. So observations made at late times depend on measurements of the state of the quantum field at short distances. In other words, what you measure way up here at a late time is determined by what there was on the horizon very close to, what there was on the initial value surface very close to the horizon. So the measurements come from the state of the quantum field at short distances. But every state is equivalent to the vacuum at short distances. So the late time observations of the observer probe the vacuum near the horizon at short distances. And that's all they probe. There's a universal answer for the late time behavior, because no matter what it was that collapsed to form the star, outside where we set up this initial value surface, we're just probing the vacuum near the horizon when we make observations at late times. So now I'm going to explain, well, Hawking's calculation was later simplified by a number of authors, notably by Turing and Haag, I think around 1988. And I'll be further slightly simplifying the way they explained it. So we introduce a function u that vanishes at the horizon on some particular Cauchy slice. I'm changing the picture now. I'm not going to draw the whole space-time that we had here. I'm only drawing the part of it that's important, the part that contains these outgoing light rays near the horizon. So, well, okay, here's the horizon. Here's the part of the singularity that's near future infinity. The black line is the far future. We parameterize the far future by the time, and t goes to infinity up here. So the observer at the far future is way up near this point and is seeing the purple lines, the signals that come out on the purple lines from very close to the horizon. So I reiterate, this is a conformally rescaled Penrose diagram, which it's been conformally rescaled so we can see what's going on. But distances are small here, and they're very large here. So the causal relations are captured in a normal way, but you have to remember that an infinite amount of time elapses up here for the outgoing observer, but there's very little space here near the horizon. Let t be the time at which a signal is detected by an observer at infinity. There's one important equation, which is the relation between u and t. So we start a distance from u from the horizon, and we go out at the speed of light along an outgoing null geodesic, or just simply along an outgoing light ray, and we arrive at the future infinity at some time t. To find what that time is, we need to look at the Schwarzschild solution. A fancy way to say it is that you solve the geodesic equation for an outgoing null geodesic. But if you're given the formula for Kruskal coordinates in the Schwarzschild black hole, you can practically read off this formula from the definition of his coordinates. Anyway, this is the one technical fact about the black hole that we need to know. And we find it by literally finding if you start a distance u from the horizon and go out at the speed of light, at what time do you get to infinity? When I say time, I really mean retarded time. In other words, what I'm calling time in the slides as I wrote them is really the retarded time. But more informally, the time at which the distant observer makes the observation grows logarithmically as the signal approaches, is given by this formula. So I didn't tell you exactly how to define u, but it doesn't matter. If you rescale u by a constant, that'll just add a constant to t because of the nature of the logarithm. And so that will, changing the units by which you measure distance near the horizon would be like adding a constant to the 0 of time as measured by the outgoing observer. And rescaling, adding nonlinear redefinitions of u will only affect terms that are even less important, terms of order u, where u will be very small. So we can solve this equation for u, and we find that if you make an observation at a time t, you're observing what there was a distance u from the horizon, where u is exponentially small in t. So at late times, in other words, if t is large, u is exponentially small. And du dt is also exponentially small. So a mode observed at infinity has undergone an exponentially large redshift. That means that a mode of any given energy E that's observed at late times originated from a very high energy mode near the horizon. That's why there's a simple answer. A mode of very high energy propagates almost essentially freely along the geodesics I've been drawing. So let's try to get back to the picture. Now you have to imagine a very high energy mode starts here. It has such a high energy, quantum mechanically, it's a wave of some kind. But it has such short wavelength that it propagates essentially along a geodesic and simply follows these purple lines. So the late observer is really seeing what originated very close to the horizon as very high energy modes. Now, the observer at infinity probes the radiation by measuring something. And in general, what you measure is a quantum field. For example, it might be the electric field or the magnetic field if you're detecting light. If you're detecting light, that means you're measuring the electric and magnetic fields of the light somehow. Let's just say we're measuring the quantum field psi. The typical observable is a two-point function. The simplest way to characterize your observations is to measure the two-point function of what you see incidence upon you. Near the horizon, suppose for simplicity that the field psi is a free fermion with dimension 1/2 in the 1 + 1 dimensional sense, where the two dimensions are the two dimensions of the Penrose diagram. So what we do is we make a partial wave expansion. So we consider a mode that has a definite dependence on the angles. It reduces effectively to a two-dimensional field. But for the reasons I've explained, it's going to be a two-dimensional field of when it's near the horizon, has very high energy. So it'll effectively be some kind of, well, we could, when we make observations at late times, they come from the two-point function of the field psi at points very close to the horizon. So we're interested in what a quantum field does. The measurements we observe come from the two-point function of the quantum field very close to the horizon. So at short distances, a quantum field will have usually a power law singularity, something like, in this example, a simple power, 1/u minus u prime. Then setting u equals a constant times e to the minus t over 4gm, we see that for the observer at infinity, the two-point function looks like this. All I did was to take a quantum field with a power law behavior near the horizon at short distances, and I transformed from near the horizon to infinity using this formula, and I got a formula for the two-point function that the observer near infinity will measure. And it depends on time like this. It's periodic and it's anti-periodic in imaginary time. It's odd under this imaginary shift of the time. And that anti-periodicity corresponds to a thermal correlation function at a temperature now called the Hawking temperature. T sub h is 1/8 pi gm, where that temperature is determined from the anti-periodicity. So in other words, this is how Hawking discovered that a black hole, after transients die down, radiates thermally at a temperature 1/8 pi gm. That explained why Bekenstein had trouble making sense of the interaction of the black hole with low energy photons. The photons he couldn't understand have an energy less than the black hole temperature. So the black hole was strongly radiating at those wavelengths. And Bekenstein couldn't make sense of the interactions of the black hole with those photons without knowing that it was emitting them. Now that we know the temperature, we can also confirm the value of the entropy. We use the E equals TdS. E is the black hole mass. T is 1 over 8 pi gm. And integrating, we learned that S is 4 pi gm squared. The area of a Schwarzschild black hole is 16 pi g squared m squared. So the entropy is the area over 4g. And that's how Hawking confirmed Bekenstein's idea and determined the constant that was unclear in Bekenstein's work. Well, ever since this work of Hawking's, many researchers have thought that somehow the entropy A over 4g means the black hole can be described by some sort of degrees of freedom that live at its surface, with 1 bit or qubit for every 1 over 4g of area. Here's a picture John Wheeler wrote in a famous article published in 1992. Although the article was published in 1992, I wouldn't be surprised if Wheeler had been drawing the picture for 20 years, ever since Bekenstein's paper. He showed a black hole horizon. He divided the horizon into small regions of area 1 over 4g, and he imagined a single bit or qubit in each horizon area. So this is what I'll say about black hole thermodynamics as the ideas originally developed in the 70s. Of course, there's a lot I'm not explaining because there won't be time. The most important thing I'm not explaining is how Gibbons and Hawking interpreted the black hole entropy in terms of the gravitational action and a Euclidean path integral. Unfortunately, we'll have to skip over that. Instead, I want to start giving a taste, at least, of a more modern understanding of the subject. So a more modern understanding of black hole entropy involves understanding what entropy means in quantum mechanics at a more fundamental level. So I want to explain the von Neumann interpretation of entropy, but as a preliminary, let's remember the general idea of a density matrix. So we consider a quantum system that's made of two subsystems, A and B. For example, A might be the lab while B might be the rest of the universe. Each system has its own Hilbert space, HA and HB. The Hilbert space of the combined system is a tensor product, HAB, which HA tensor HB. The whole system might be described by a pure quantum state, psi AB, a vector in HA tensor HB. If that's the case, we can define the projection operator onto psi, which is called a pure state density matrix. In a moment, I'll remind you what a density matrix is that aren't associated to pure states. But the projection operator onto psi is called a pure state density matrix. And now we can see that the expectation value of any operator O in the state psi is the same as the trace of O times the density matrix. In writing this formula, all I did was to take the bra from the left and move it over to put it in the ket. So if you move the bra over to the ket, if you literally just move psi from the left to the right, you would write this expression. But this expression is a product of two operators, namely O, and one of the two operators is O. The other is the projection operator, rho AB, onto psi. So now if you take the trace of this product of operators, that'll compensate for the fact that you move the bra over to the right, and it will give you the same thing as the expectation value of the operator in the state. Now, we notice in this example that rho AB has some properties that come from the projection operator onto a pure state. Its Hermitian, non-negative, and its trace is 1, where the last statement holds because rho is a rank 1 projection operator. However, suppose we're only going to observe the subsystem A. That means we consider only operators of the form something acting on system A tensored with the identity on system B. Well, as I said, the explanation of any operator in the state psi AB is the trace of that operator times rho AB. Here we assume the operator acts only on A, so it has this form. But now, since we have only the identity operator acting on B, we can take the sum over all states in B. So the trace over AB could be thought of as a trace over A and a trace over B. In other words, trace means sum over states. You can do that in two steps. First, sum over states of B, then sum over states of A. Since O is not acting on B, the trace over B is something simple. It's called a partial trace. You sum over all states in B and get what's called rho sub A, the density matrix of system A. And so doing this partial trace over B, we can write a formula for the expectation value of the operator of this form in the state psi AB that only involves system A. Instead of taking the trace of OA tensored the identity in the big Hilbert space, we can eliminate the degrees of freedom of B by doing this partial trace here. And then we get a reduced density matrix, it's called, that only acts on system A, such that the expectation value is the trace of the operator that we're interested in on system A times rho A. In other words, for measurements on system A only, we can use the density matrix rho A that we obtained by a partial trace on HB. So the definition immediately assures that rho A is Hermitian non-negative and has trace 1, just like rho AB, but it does not necessarily have rank 1. Rho A has all the properties of a pure state density matrix, except it doesn't have rank 1. If psi AB is what's called an entangled state of systems A and B, which means psi AB is something like this. It's not a simple product of a state of A times a state of B, but a sum of such products. Then, if that's the case, we say that psi AB is entangled. And in such a case, rho A has rank bigger than 1. Now, suppose we're only going to observe the sub. So almost every state of the combined system is like that. Almost every state is entangled. So this will serve as a starting point to discuss entropy at the quantum level. Let's remember entropy classically first. The original definition of entropy goes back to Boltzmann. He considered a system of n particles in a box with positions x and momenta p. As a classical physicist, Boltzmann assumed that at a given time, x and p have definite values, even if we don't know them. And then you can describe the state of your knowledge by a probability distribution function, rho of p and x. So after great labor, Boltzmann and followers such as Gibbs defined the entropy as the phase space integral of minus rho log rho. So in a previous version of this lecture, I attributed the formula to Boltzmann, but I've learned since that it's more accurate to attribute this to Gibbs. Boltzmann had precursors of this type of statements. Anyway, that's a classical definition of entropy. For a quantum system, the density matrix is the closest analog of the classical probability distribution function. To see that, recall that if a system has a density matrix rho, the expectation value of an observable is the trace of the operator times rho. We can always diagonalize the Hermitian matrix rho with eigenvalues lambda j for some lambdas, and therefore the expectation value of the operator is the sum of lambda I times OII, as if this system is in state I with probability lambda I. The interpretation makes sense because since rho is non-negative and its trace is 1, the lambdas are non-negative and their sum is 1. So the lambdas behave as probabilities. So the quantum analog of integrating over phase space is to take a trace, and the quantum analog of the density of the probability distribution function is the density matrix. I've called them both rho. So the quantum analog of Boltzmann's integral is the von Neumann entropy minus rho log, trace of minus rho log rho. In the classical limit, the von Neumann entropy goes over to the classical entropy, plus an additive constant that depends on h bar and is poorly defined classically. If the eigenvalues of rho are the lambdas, the entropy is minus the sum of lambda log lambda. And then if you know the state of a system with certainty, if one of the lambdas is 1, the others are 0, which means that rho is rank 1. For a pure state density matrix, the formula gives S equals 0. Otherwise, every lambda makes a positive contribution, or every non-zero lambda makes a positive contribution. So the entropy is strictly positive. If a system is entangled with something else, rho has rank greater than 1 if the entropy is positive. So this is the quantum generalization of entropy, but there's a fundamental difference between the classical and quantum cases. Classically, you assume x and p have actual values, and you describe the system by distribution function because of lack of knowledge. Quantum mechanically, a system can have an entropy, even if we understand its state as well as quantum mechanics allows. That happens because of entanglement. As I've explained, if A and B are two quantum states in an overall pure state, but that state is entangled, then the density matrix, even if the overall state is pure, if psi is entangled, rho A has a density matrix of rank greater than 1 and a positive entropy. If A and B are entangled, this could be verified experimentally. There's no way to describe system A by a pure state density matrix with 0 entropy. So quantum mechanically, there's an irreducible entropy that doesn't depend on our ignorance, but comes from quantum mechanics. Of course, just as classically, we might not know the state of a system as well as quantum mechanics allows. Then we use a density matrix that reflects our knowledge. Just as classically, we use a probability distribution function that reflects your knowledge. For example, if you know nothing about the state of a system, you could take rho to be a multiple of the identity, though someone else who might know how it was prepared might describe it by pure state. If all you know is the temperature, you use a thermal density matrix. And then in such a situation, the von Neumann entropy is the thermodynamic entropy, a familiar concept classically. What's important about this, though, in part, is that thermodynamic entropy is a notion that only makes sense close to thermal equilibrium. But von Neumann entropy always makes sense for any quantum system. So von Neumann entropy generalizes quantum entropy to something that's always defined for any quantum state. As I've stressed, what's different about quantum mechanics is the entropy that remains if you know the state of a system as well as quantum mechanics allows. This has been called entanglement entropy because it comes from entanglement. It's also been called fine-grained entropy. Well, why have I spent so much time reviewing the von Neumann entropy? The idea that the Bekenstein-Hawking entropy is entanglement entropy apparently goes back to a paper by Raphael Sorkin in 1983, a paper that attracted only modest attention at the time. The idea was the following. In a quantum field theory, divide space into two regions, A and B. Let psi be some state. I wrote the vacuum state. It could be any state, but the vacuum state is a good example. Then, of course, this state has a pure state density matrix. First of all, psi is a state of the combined system. Like any state, it would have a pure state density matrix. And that pure state density matrix could be used to describe observations anywhere in space. But suppose you're only going to make observations in one region. For example, region A. Then you can try to construct a density matrix appropriate for measurements only in region A. And you can try to calculate its density, its entropy. Well, Sorkin discussed this and found that it's ultraviolet divergence. The ultraviolet divergence comes because there's a lot of entanglement between short wavelength modes just in region A near the boundary or highly entangled with modes in B near the boundary. But the ultraviolet divergence is proportional to the area A of the boundary between the two regions A and B. So he got an entropy, the entanglement entropy between the two regions, that was proportional to the area, unfortunately with an ultraviolet divergent factor, a factor that's infinite in ordinary quantum field theory. To state his idea a little bit closer to modern language, it was that somehow gravity cuts off the ultraviolet divergence, leaving an entanglement entropy between the two regions. That's the area not times infinity, but the area times 1 over 4G, where A is the area of the boundary between them, and G is Newton's constant. Now, this makes a lot of intuitive sense as it matches two ideas. First, Bekenstein's intuition was that A over 4G is the irreducible entropy of the system for someone who only has access to the region outside the horizon. So that intuitive notion of Bekenstein's is sort of captured by Sorkin's idea. Two, the divergence Sorkin found in the entanglement entropy was proportional to the area because it comes from very short wavelength modes near the horizon. As if the density of quantum degrees of freedom on the horizon, well, it's as if, as in Wheeler's picture, there are quantum degrees of freedom on or very close to the horizon with entanglement between inside and outside, naturally producing an entropy per unit area. Because in every little area element, there's a degree of freedom inside entangled with one outside. So the divergence being proportional to the area was in the spirit of Wheeler's picture. So this was Sorkin in 1983. You could think of it as the first step toward a more modern understanding. Another big step toward a more modern understanding was made a decade later by Susskind and Uglum. They made an incredibly simple but deep observation that strongly supports the idea of interpreting the entropy outside the black hole as entanglement entropy. Okay, so let's take a step back. Let's now remember Bekenstein's formula. So the generalized entropy was the area over 4G. But Bekenstein hadn't said exactly what's meant by the entropy outside the black hole. He imagined it was entropy defined thermodynamically. But Sorkin said, no, you can't. There's a problem with that, which is that not every state is in thermal equilibrium. So what did Bekenstein's formula mean if something that isn't in thermal equilibrium falls into a black hole? To make sense of the formula, you need to use a notion of S out that's always defined, not just if the system outside is in thermal equilibrium. And Sorkin had made use of a notion of entropy that doesn't require equilibrium, namely the von Neumann entropy. Always defined. So part of what Susskind and Uglum did was just to reinterpret Bekenstein's formula so that S out was always meaningful. They did that by simply saying that S out is not the thermodynamic entropy outside the black hole, but the von Neumann entropy outside the black hole. Those are the same if the system outside the black hole is in thermal equilibrium. But the von Neumann entropy has the advantage that it's always defined. So they interpret the entropy outside the black hole as entanglement entropy. And then they made an incredibly simple but deep statement that the generalized entropy is better defined than either piece is separately. Why? Well, the second term is what Sorkin had studied. Here's in and here's out. And Sorokin had found an ultraviolet divergence in the entanglement between the inside and the outside of any surface. In particular, it works fine if the surface is a black hole horizon. So S out has an ultraviolet divergence. Well, why is that good? For a decade after Sorokin, nobody made the following simple observation about why it's good that S out has an ultraviolet divergence. A over 4G H bar also has an ultraviolet divergence because Newton's constant does, because gravity has ultraviolet divergences. So there's an ultraviolet divergence in the relation between the bare Newton constant G naught and the physical observed Newton constant G. In one loop order, the relation is this one. 1 over G H bar is 1 over G naught H bar plus a constant times lambda squared. Now, I sketched earlier, well, a slightly simplified version of Hawking's derivation of black hole entropy. And I wrote the answer as 1 over 4G H bar. But if you think about it a little bit, you'll see that the G in that discussion was the bare G, because we didn't discuss anything that would normalize G. So we should have written the answer we got as A over 4G naught H bar. And then we should have considered quantum loops that would have renormalized the parameters in our discussion, and they would have been divergent. And we'd have gotten a relation like this one. So in fact, both terms in the formula are ultraviolet divergence. And Susskind and Uglum argued that the ultraviolet divergences in S out cancel those in 1 over G. And this is accepted today. Later authors refined the arguments, but the basic idea is as Susskind and Uglum said. So after this, it was kind of clear that S out, at least, had to be interpreted as von Neumann entropy in order to make this formula ultraviolet finite. But it also had the advantage that now the formula makes sense for all quantum states, not just, you no longer have to assume that the quantum system outside the black hole is in thermal equilibrium. So this interpretation now has two advantages. The right-hand side is always defined, and it's ultraviolet finite. 21st century developments have supported all these ideas, but leaving plenty of mysteries. And I'll use the remaining time to give just a few hints about some of the developments. What I'm going to do is to mention, but unfortunately not with a lot of time to explain in detail, a couple of later developments that were possible because entropy was understood as von Neumann entropy. Bekenstein went back to the generalized second law years later and asked whether it's satisfied when a body of mass m and therefore radius 2 gm absorbs a body of curly r, size curly r, energy E and entropy S. The entropy disappears, so the generalized second law says that the increase in the black hole entropy must be more than that. We already computed that the black hole entropy changes by this amount. So we'd like this inequality if the black hole can absorb the given body. Now, if you naively say that a black hole of Schwarzschild radius 4 gm can only absorb a body of size curly r if curly r is less than 4 gm, then we get this desired inequality. Note the formula makes no mention of gravity or Newton's constant. It's potentially just a statement about ordinary quantum physics without gravity. Now, the derivation isn't entirely convincing for a lot of reasons. For example, maybe the outside body gets crushed before it falls into the black hole, or maybe it gets torn apart and it falls into the black hole in pieces. So it's by no means clear that it's true that a black hole can't absorb a body that's too big. In fact, in general, it's not true. So from the derivation, it's not clear you should believe this formula. Nevertheless, over the following 30 years, Bekenstein's proposal that there would be a bound like this, relating the size, energy, and entropy of any system, attracted a lot of interest. Now, there were two questions that come immediately to mind. So, faced with a conjecture like this, where the conjecture is that there's universal inequality that says energy times size is bigger than entropy times some constant. One question is the statement true? And the second question is, if true, is it interesting? For years, there was lots of skepticism on both counts. In fact, I was one of the skeptics. I thought the answer was no on both of these questions. So first, on the question of whether the Bekenstein bound is true, there seems to be a trivial argument that it's not, at least not as a universal statement about all quantum field theories. Consider a theory with n elementary particles all of the same mass. For example, a free field theory with n particles, n fields. Consider a system consisting of a box that contains one particle. The entropy seems to be at least log n because we chose one of n particles to put in the box. But the size and energy of the box don't depend on n. So it seemed clear the Bekenstein bound isn't a universal statement in quantum field theory. On the other hand, if true, is the Bekenstein bound interesting? Well, to be interesting, for an inequality to be interesting, it should sometimes be close to being violated. If the inequality is always saturated with many, many orders of magnitude to spare, it's not a very incisive statement. So is there a system that comes close to violating the Bekenstein bound? Consider a system made of massless particles. If you give them masses, that increases the energy, without increasing the entropy, so it makes things worse. For example, consider a box of size curly r that contains a gas of massless particles at temperature T. In 3 dimensions, the number of particles in the box is of order RT cubed, and that's the order of magnitude of the entropy. The energy is r cubed T to the 4th. So the Bekenstein ratio S over RE, on which we want an upper bound, is 1 over size times temperature. If size times temperature is large, the notion of a thermal gas in a box makes sense. But in that case, S over RE is much less than 1, and the Bekenstein bound isn't that interesting. How do we find a system for which the Bekenstein bound is interesting as well as true? Well, if we keep many particles in the box but assume they're not in thermal equilibrium, that makes things worse because it lowers the entropy for given energy. To make the bound challenging, we have to reduce the number of particles, which we can do by lowering the temperature. The best case is that the box just contains one or a few massless particles. In other words, that the temperature is of order 1 over the size. But a box containing just one or a few particles will weigh more than the particles it contains. So now we can't ignore the mass of the box, which maybe was unimportant when there were many particles in the box, but not if the box is almost empty. Including the mass of the box goes in the wrong direction and makes the Bekenstein bound uninteresting. In other words, the case that the Bekenstein bound is interesting is the case of a single particle without a box. But what sense does the Bekenstein bound make in that case? What's the entropy of a single particle? For that matter, what's the size of a system consisting of a single particle? In other words, when we try to go to a regime in which the Bekenstein bound is interesting, the statement of the Bekenstein bound does not seem to make sense. Amazingly, Cassini was able to give a precise definition. This is Horacio Cassini, was able to give a precise definition to the terms in the Bekenstein bound and to prove it. He used one more fact about density matrix that I haven't mentioned. Let sigma and rho be two density matrices on the same Hilbert space. Something called the relative entropy between them is defined this way. It measures in what turns out to be a useful sense how different they are. For now, what we care about is that the relative entropy is always non-negative and vanishes only if sigma equals rho. I've given at the last part of this slide a quick sketch of how you prove that. But I don't want to go over the steps right now. But there's a simple computation with matrices that you can read later. If, for example, these slides are posted on a website, that explains that the relative entropy is always non-negative. So what two states did Cassini consider? He took one to be the vacuum state, and then the other was any state psi. The Bekenstein bound was supposed to be a universal statement of quantum field theory. So it's supposed to be true for any quantum field theory in any state. So for psi, he took the state in which you want the Bekenstein bound to be true. And then he considers what's called Rindler space. So here's Minkowski space, except I've only drawn two coordinates. A spatial coordinate x runs horizontally, time runs vertically. The regions A and B are called left and right Rindler wedges. So now, Cassini considered the Rindler wedge A. He considered an observer living in region A and only making measurements in region A. And then he considered density matrices rho, psi, rho, and sigma of the states psi and omega reduced to region A. The relative entropy between them determines how well psi and omega can be distinguished if you only make measurements in region A. We have positivity of the relative entropy. So the relative entropy was defined for all quantum states because it has a microscopic, oh my gosh, I got out of, okay. It has a microscopic definition just in terms of the density matrix. The definition of the relative entropy was like the von Neumann entropy, of which it's a slight generalization. It's defined for any two quantum states, irrespective of whether thermodynamics would be valid. And because it was, he got a universal statement, which he showed as a version of the Bekenstein bound, that ER is at least 2 pi times S. So he got, well, he had a S, and he showed S is the von Neumann entropy. Well, he gave precise definitions of all the terms, such that this formula turns into a version of the Bekenstein bound. I don't want to say too much more about that because I want to sketch another result in a similar spirit. A deeper one, probably inspired in part by this result, proved a few years later by Aaron Wall. Remember, Bekenstein had conjectured a generalized second law, that the generalized entropy always increases. Well, is it true? For ordinary matter with a black hole, interacting with a black hole, the bound is uninteresting in the same sense that the Bekenstein bound is uninteresting. If you really toss a cup of tea into a black hole, S out goes down, A over 4 GH bar goes up. But A over 4 GH bar goes up by much more than S out goes down. That's not unlike the fact that the entropy of a black hole with the mass of the sun is vastly more than the black hole of the actual sun. So, just as in the case of the Bekenstein bound, if you want to find a situation that really challenges this, you have to work a little bit harder. To seriously challenge the generalized second law, you need to consider a general state of a quantum field in conditions in which thermodynamics don't really apply. If you go to a situation where thermodynamics applies, then the cup of tea is potentially an example. The cup of tea might have been a system to which thermodynamics applies at some temperature. When thermodynamics is good, you'll find that the change in this is much bigger than the change in this. So first, you should go to a situation where thermodynamics is not necessarily valid and consider an arbitrary state of the quantum fields outside the black hole. Secondly, you should have a black hole that's stationary classically. So stationary classically means that A dot is 0 classically. which means that in real life, A dot will be of order h bar with quantum corrections. And then you see that the change in A over 4g h bar will be of order 1 because the change in A is of order h bar. The entropy outside will also be of order 1. So if you have a black hole that is stationary except for quantum corrections, and a general state of quantum matter outside the black hole where thermodynamics doesn't necessarily apply, then you're in a situation where you can really challenge the generalized second law and ask if it's true. To seriously probe the generalized second law, we have to probe it with a general state of a quantum field where thermodynamics doesn't really apply. But we know what to do. We define S out as the von Neumann entropy of the quantum fields outside the black hole. So the most interesting case is the case that is stationary classically, as I told you. But the back reaction of the quantum fields can cause an order h bar term in A dot, the time derivative of A, so an order 1 term in A dot over 4g h bar, except that this should be a capital G. And that A dot term, order 1 term in A dot over 4g h bar can compete with the change in S out. We want to prove that A dot over 4g h bar plus S out dot is equal to or greater than 0, where the dot is time derivative. So Wall proved this, but I'm only going to be able to give you a few hints of what he did. The first step, well, U is meant to be an initial value surface on which the outside observer is measuring the quantum state, and therefore the entropy. And here I didn't continue the initial value surface behind the horizon, because we're looking at the world from the point of view of the outside observer, who only sees the part of U outside the horizon. Now, to define SGen, well, we have A over 4g h bar, but of course we have to take that here. If the entropy is defined on the surface U, then the area should be taken at the end of U. So SGen is defined on the surface U. Now, when we say that SGen can only increase, we mean that if we made the observations at a later time, SGen would be bigger. So here's a picture of a later time. Here's another hypersurface V, also space-like, where the observer might be making observations. And it intersects the black hole horizon at a later time. Now, an important observation of Wall, okay. So a key observation is that the cut of the horizon, so there's really in this picture a region of space-time. You take the time at which you're going to study the black hole horizon. That's given by what's called a cut of the horizon. Cut of the horizon is just jargon for the time at which you want to measure the area. Whatever that time is, you connect it to spatial infinity by a space-like surface, here drawn as U. It doesn't matter which surface you pick, because the green region is what's called the domain of dependence of U. The green region is the region in which your observations are determined by initial data on U. So traveling slower than light, anything in the green region came from U. So we could think of SGen as associated to this time on the horizon, or we could think of it as being associated to this this partial Cauchy surface of the outside observer. But an elementary but very important insight of Wall's is that we could think of SGen as being associated to this entire green region, because a time on the horizon determines that green region. Likewise, the later cut also determines a green region, but it determines a smaller region. So this was a key observation of Wall's, that each time on which you want to measure the generalized entropy determines a space-time region in which you're studying the entropy. But the later is the time, the smaller is the region. So Wall showed that Sgen is actually the relative entropy. Wall had this wonderful formula that Sgen is the relative entropy of the state in which you're trying to probe the generalized second law with the given Hawking state. The relative entropy for the region outside the horizon determined by you between those two states. And when you make the observation at a later time, you're considering the generalized entropy in a smaller region. So to show that Sgen in the later region is bigger than Sgen in the earlier region, because of the relation that Wall discovered with relative entropy, there's a minus sign in the relation of Sgen and relative entropy. So the inequality has to go in the opposite direction. So Wall turned the generalized second law into a statement about relative entropies. And happily, the statement is true because of a very deep result of Lieb and Ruskay, which implies that the relative entropy between two states becomes smaller if you reduce the region in which you compare them. So Aaron Wall's remarkable discovery was that this rather deep property of quantum entropy, which was discovered at almost the same time as Bekenstein's original paper. 40 years later, Wall made the connection between these two papers and showed that this deep property of quantum entropy in this context leads to the generalized second law. In summary, I've tried to give a basic introduction to the original ideas of black hole thermodynamics from half a century ago, and I've tried to give at least a few hints of the way that a more contemporary thinking is based on a more microscopic understanding of entropy. I regret not having said more. I told you a few highlights. In fact, I explained 4 highlights. There was Sorkin, Susskind and Uglum, Cassini, and Wall. I haven't been able to, unfortunately, tell you about any of the even more recent highlights, of which there have been many, but I hope to have at least given you an idea of the fact that the modern understanding goes well beyond what was understood in the 70s, and in fact has become a very exciting subject. Thank you very much.
Thank you so much, Professor Witten. Let's have a round of applause. I don't know if you can hear it. So with your permission, can we have a brief Q&A session? Will that be all right?
Sure, go ahead.
Okay, great. So I'm going to be partial, and I'm going to take up a query that came in from the folks sitting here, and then get onto the chat query. So if I can trust WhatsApp, this somebody by the name of Devarshi, and the query is, since there is a direct relationship between entropy and area, can we say that the classical space and time dimensions are in fact a superposition of wave functions with different probability amplitudes? And there is a good evening there.
Well, somehow we think that quantum mechanics applies to space and time, but we certainly can't give full answers to that kind of question. The deepest insight really comes from ADS-CFT duality, which would have called for a different lecture from today, where we understand space and time as being emergent from an ordinary quantum system in the boundary of space-time. I think I'm going to have to say in spirit yes to your question, but in detail, certainly we don't understand anything.
Okay. So there was a question by Ajay, and the question is, so Stephen Hawking says that at the quantum level, the black hole is not black. It is proportional to the Planck's constant, that is angular momentum. But quantum mechanically, the black hole possesses rotation, and rotation connects with magnetic moment. So
Yeah.
does the magnetic moment contribute to the quantum mechanics at some state?
Well, first of all, if a black hole has a black hole was definitely the magnetic field of the black hole, or the region around the black hole is very important. So in vacuum, a stationary black hole that's spinning and has electric charge would also have a magnetic moment. But usually the charge of the black hole is not very important, but the plasma, the magnetic field is very important. In an astrophysical situation, the magnetic field of the black hole is extremely important because there's usually a conducting plasma outside the black hole. And the magnetic field is an important part of the mechanism by which energy is extracted from the black hole. I think that's all I can really say now.
So Deepan Betal has a couple of queries. First is, what is the effect on the late time probing of the near event horizon vacuum due to a cosmological constant?
The cosmological constant is very, very important at long distances, but it's not very important at short distances. So the analysis I gave, I drew the Penrose diagram for a black hole in Minkowski space, but the same general idea would make sense for a black hole in de Sitter. Well, the same general idea holds for a black hole in a space with a cosmological constant. What's different is really the way you describe the observer at infinity is different, but the physics near the horizon is really not changed.
Okay. Deepan has another query, and it says, is there any notion of von Neumann entropy for multipartite entanglement?
Well, von Neumann entropy doesn't completely characterize the nature of entanglement. Von Neumann entropy is defined for any system. So let's try to discuss what the question is. So the question, you imagine three systems, A, B, and C. Then you might or might not have a pure state psi ABC, but in any case, you have a tripartite density matrix rho ABC and various reduced density matrices. You can define a lot of density matrices in this situation. You can define a von Neumann entropy for each of them. I think what you're really getting at with the question is there a good way to describe by tripartite entanglement quantitatively by something similar to von Neumann entropy? There isn't anything as nice as von Neumann entropy that really captures tripartite entanglement.
Okay. See. So will these same, as Kumar Ashutosh has a question, will these same ideas also apply to white holes?
Well, I'm torn between several possible answers. So one answer is that in the real world, black holes can form. But as far as we know, okay, Penrose's cosmic censorship appears to be valid as far as we can tell from numerical experiments, although it certainly hasn't been proved. So as far as we know in the real world, we can form black holes and not white holes. So we believe that Hawking radiation is a phenomenon about black holes that could happen in the real world. It's not quite clear what we should ask about white holes. The best analog of a white hole in the real world, I guess, would be a cosmological singularity that we don't understand too well. Maybe I should give a yes answer on the grounds that particle creation from the cosmological horizon is somewhat similar to Hawking's particle creation from a black hole. That's the best I can do to give a yes answer to your question.
Okay. Okay, Ajay has another query. It says, he says, is the law of increase of entropy dimension dependent?
No. Aaron Walls analysis of the generalized second law. It didn't depend on the space-time dimension.
Okay. Deepan Betal has, in fact, a third query. He asks, does a change of the quantum vacuum near the event horizon cause any changes through tree-level gauge processes? And is that observable through black hole temperature at null infinity or some notion of quantum entropy?
Well, the most interesting thing that your question inspires to me is what happens if you're interested in Hawking radiation of hadrons. So that's a tricky question because at very high energies, you could treat the quarks and gluons as free particles. So my discussion would appear to apply to radiation of quarks and gluons from the black hole. But obviously at long distances, they don't behave as free particles. So in reality, the Hawking radiation of strongly interacting particles is radically changed by the nature of the vacuum at a distance of order 1 over lambda QCD from the black hole horizon. So that's the best I can say in response to that question.
Okay.
So,
all right. Deepan has one last pair of queries. So the first says, and I think we'll conclude with that, with a pair. So could there be tunneling between primordial black holes where the Compton wavelength is more than the event horizon radius? And how does that affect the entropy?
I'm not sure I really have anything useful to say.
Okay, maybe we can go to the last query again by the.
Yeah.
It says, is there a Casimir effect for black holes?
Well, you could think of Hawking radiation as the analog of the Casimir effect. The Casimir effect has to do with the energy of the vacuum, right? But the Hawking effect, so usually you have electrically charged plates, well, dielectric plates or electrically charged plates or something. There's a space between them. You study its quantum ground state. And usually in the Casimir effect, the quantum ground state is stable, but you compute its energy density. Here, the Hawking effect says that the quantum state outside the black hole is unstable, it radiates. So I would say that the Hawking radiation is a more drastic analog of the Casimir effect.
Okay, so folks, I think with that, we come to the conclusion of this incredible C.V. Raman Memorial Lecture by Professor Witten. Let's maybe once more thank him for his incredible patience with the queries. So, thank you.
Thank you again for the invitation. Good luck, everyone, and be well.
Please stay safe. Bye-bye.
Bye-bye.
Okay, so all right, folks, so that's it. I mean, we come to the conclusion of the session conclusively. So thanks. Maybe we can have a greater turnout tomorrow. I think there is a conflict of music versus physics today. We know who wins. So I think, team, let's end everything. Let's end the Zoom recording. Let's end the YouTube live. I hope that last remark would be edited out.
Sure, Professor.
Thank you, team. Thank you so much. ठीक है, शुभ रात्रि. हो गई. Okay, bye-bye. So I'm ending the meeting now, right?